Welcome back, you guys. I hope your study of the integral test was successful and is continuing. We're going to add to that toolbox now with two comparison tests. One is known as a direct comparison test, or sometimes just comparison test. And the second, the limit comparison test. So here we go. Okay, so here's what the comparison tests say. You have two series. Again, positive terms. If the series Bn converges and all the ANs are less than or equal to Bn, then my series AN is also convergent. If my series Bn diverges and my ANs are greater than or equal to the Bns, then my series AN is also divergent. Here's what's really going on. We're going to prove this, but you might think of it this way. You've got some convergent series. So Bn, the sum Bn is finite, which means the ANs, right, have to be finite as well, right? If I essentially have put a ceiling on the Bns and the ANs have to live below the Bns, then they can only get so far, okay? And we're talking about positive terms, right? So I'm adding these positive terms, but they can't exceed this value. They must converge. Now, on the other hand, if the Bns, what a horrible summation sign, there we go, is not finite, then you could think of it this way. You've got a floor, and that floor is pushing up. And all your ANs, your partial sums for the AN series, live up here. And so if they just keep getting pushed up and up and up and up, they're going to diverge as well. Let's give some proof to this, shall we? All right. So the first one. So this is my proof. We're going to start with the first case. So I'm going to let, right, I need to get my hands on these partial sums. So I'm going to let Sn be the partial sums for my AN series. And then my Tn be the partial sum for my B series. Now, any guesses where we're going to go with this? Well, my picture, previous slide, kind of hinted at it. We've got boundedness. If only we could show monotonicity as well, right? Bounded above and increasing, then we'll be golden. So let's take a look what we know. We know that the AIs and the BIs are all greater than 0, which means that my partial sums are increasing. Right? Think about it. You're adding positive terms over and over again. The more positive terms you add, the larger the sum. Now, we know that the Tn's converge, and we know this, that partial sum is going to be less than or equal to whatever the actual sum is. And so I'm going to give that a name and call that capital M. Okay? Now, let's take advantage of the fact that the AIs are all less than or equal to the BIs. Well, that tells me that Sn, my partial sum for the A's, is going to be less than or equal to my partial sum for the b's, which is less than or equal to this m for all n. Well, what does that tell me? That tells me that my partial sums for AI, or my AN series, is bounded above, right? That sum's smaller than some other sequence of partial sums, which is bounded above, so my SNs must be bounded above. Okay, well, again, increasing, bounded above. So by my numbering, theorem 11.1.5, bounded monotonic theorem, my series AN must converge. Okay? All right. So let's now take a look at the second piece, divergence. So this diverges then we know this just approaches infinity, since that sequence partial sums is increasing, right? We have positive terms, we keep adding and adding and adding, so if we have divergence, they must be blowing up to infinity. Well, we also know that AI is greater than or equal to BI. So I have Sn greater than or equal to Tn for all n. And so what does that tell me? Well, this thing below, the Tn's, are going to infinity. So those are pushing the Sn's higher and higher and higher. Okay. Well, what does that mean? It means my series diverges. Okay. Now, what's really nice about this is that you may have a really messy looking summand or sequence that you've turned into a series. It may just, the ANs might be really gross looking or complicated. But if you can find a different series and different sequence whose terms are quite nice and you know the behavior of, then you can use that one to decide what's going on with this, your series in question. Common choices for comparison: P series, geometric series, right? We know that the P series converges for P greater than 1, diverges for P less than or equal to 1. And the geometric series converges for absolute value R less than 1, diverges otherwise. Okay? All right, so let's put this into practice here. Determine if the series converges. So the first one I want to do is the sum 1 to infinity, 1 over square root of n, 3 to the n. Well, for n greater than or equal to 1, one over square root of n times 3 to the n is going to be less than 1 over 3 to the n, right? Because those square root of n's, those are all larger than 1. So this denominator is going to be greater than that denominator? Well, greater denominator, smaller quotient, okay? So what we can do is then look at the series 1 over 3 to the n. Well, that is convergent. Why? Well, it's a p-series. I'm sorry, what am I saying? It's a geometric series with r equals 1/3, which is certainly less than 1. And so by the comparison test, my other series converges, okay? How convenient. That's a much nicer series, okay? Let's try it again, whoops. How about sum 1 to infinity 1 over n squared plus 3 to the 1/3, okay? No, I'm sorry. N equals 2. Okay. Well, for n greater than or equal to 2, I want you to notice something. And yeah, there's some creativity here, but let's kind of go with it. So this is n squared plus 3. The smallest value, the right side of this inequality, is n squared plus 4. Right? Which of course, this is 2n squared. All right. Well, if n squared plus 3 is smaller than 2n squared, right? Then I can also say this, n squared plus 3 to the 1/3 is less than 2n squared to the 1/3. Okay. Which also tells me, as quotients now, right? The larger denominator is going to be a smaller quotient. Okay. So now notice so it's 2 to the 1/3 n to the 2/3. This is a divergent p-series. How do I know? Well, my p is 2/3. Whoa, which is lacking in penmanship. My p is 2/3. It's less than 1. And so again, by the comparison test, we have that my series n squared plus 3, 1 over n squared plus 3 to the 1/3 is divergent. All right, so there we go. All right, well, we have another comparison test. It's called the limit comparison test. And this one's even nicer in some ways because you don't have to worry about one sequence being, bounding the other from above or below. You can look at the ratio, okay? And as long as you know the behavior of one of them, you know the behavior of the other. Okay, so again, my conditions, positive terms, and this limit has to be greater than 0. If it is, then both series have to do the same thing. So what I'm going to do, I'm going to prove this, and I'm going to say, I'm going to take two positive numbers, little m and capital M, and I'm going to find them such that C is trapped between them. And so what this means is, because the limit is equal to C, I can find large enough n's, meaning far enough down in the sequence, for large enough n, an over bn is trapped between little m and capital M, okay? Which then bounds an below by m little m bn and an above by capital M bn, okay? Well, comparison test. If my bn's converge, then so does, whoops, then so does, wrong color. Right, if my bn's converge, then since m is just some finite value, this series converges. And so this series, the an's, converge or converges, okay? Similarly, if my series bn diverges, well, then so does little m bn, right? It's just a constant. And so now we're pushing the an's from below off to infinity. And so I know that my an's must, or my series an diverges, okay? All right, and again, or maybe not again, but keep in mind, when you use this limit comparison test, pick a series you know the convergence of, okay? That's the whole point. All right, so let's see how this plays out. My first example here, I have the sum n equals 2 to infinity, n squared over n to the fourth minus n minus 1. Now, when I look at this, let me clean up this. When I look at this series and the sequence inside it there, you know, looking at dominant term analysis, I really see something that starts behaving like n squared over n to the fourth. So I'm going to let bn be 1 over n squared because those seem very similar. And so let's take the limit now as n goes to infinity of, well, n squared over n to the fourth minus n minus 1 all over 1 over n squared, right? An over bn. And let's see what we wind up getting here. Well, we get n to the fourth over n to the fourth minus n minus 1. And again, what's going to happen is just by dominant term analysis, right? If you want, remember that old Calc 1 technique, divide every term by n to the fourth. And so, right, that goes to 0, that goes to 0, you get 1 over 1. This is 1. And what's significant about that is that the limit exists and it's greater than 0. So by the limit comparison test, And since my series 1 over n squared converges, right? P series, p greater than 1. I know that the series in question also converges. Okay. Let's try one more. So sum 3 to infinity 1 over square root n squared plus 4. Now you might pause it and just kind of ask yourself, what might a good choice for Bn be? Well, come back. What I like to do is ask myself, what is the sequence 1 over square root n squared plus 4 starting to look like? Well, it's starting to look like 1 over n. And what do I know about 1 over n? Oh, I know it diverges. So I'm going to let Bn be 1 over n. And then see what happens. Limit n goes to infinity. 1 over the square root n squared plus 4 all over 1 over n. And so you have n over square root n squared plus 4. And again, right, dominant term analysis. The plus 4 starts to have very little effect on n squared when n's are really large. So that denominator starts looking like the square root of n squared, which means the quotient starts looking like n over n, which is just 1. And so by limit comparison test, my series diverges. Again, they have to have the same behavior. All right. So hopefully that made sense. And, you know, I would really encourage you to spend some time digesting the proofs. There's a lot in there. You know, I don't want to downplay the importance of opening up a textbook and working problems. That's very, very important. The practical nature of mathematics lends itself to being able to do procedures, right? There's a procedural component that's important. And you learn a lot through the procedures because you see the application of the theorems come alive. However, I would caution you, as wonderful a tool as calculus is, and mathematics in general, you will find it most rewarding when you get your hands dirty with the very fabric of the subject. What are the deep concepts and how do we establish them and show that they are mathematically true? Spend some time digesting the proofs. I don't expect you to watch this and say, oh yeah, I totally get it. But being able to digest and make my proofs your own will make the subject just come alive. And who knows, maybe you'll turn into a math major. So with that, enjoy this other addition to your convergence toolbox. We got the integral test, we got 2 comparison tests, and when we come back, we will look at yet some more tests. All right, until then, happy studies, happy marinating, and I will see you soon.